we were trying to find what's called the spring constant of a pop-up toy. In real life, you probably wouldn't do that unless you're some like weird, super nerdy kid. You would just have a lot of fun, okay? But in real life, measuring the elasticity of materials is very important. Probably more for like a car, suspension system, for the mattress of your bed, the bounciness of your Nikes, whatever, okay? So really, it's all about your picture. I know that sounds weird, and a lot of people find this extremely irritating, but it's really picturing what's going on. Because once you picture it, you can figure out the energy involved, and then you just set the energy equal to each other. That's it. The initial and final conditions. It's really that simple, but not. It takes a little bit of practice, okay? There was 2 methods to do the lab, and I'm not sure which one you picked. Method 1 was a simple one, where you flex the pop-up toy on the ground, and you put it on the table there. Then, when it pops up, it flies in the air, and the trick is you just really want to catch it at its highest point, because then all the energy has been converted to just one form there. So on the picture, it's not just drawing like a silly little sketch, it's figuring out the energy. So think about it. Your muscles first do work. So yes, there is work energy, but we're not going to try to measure that force over distance, okay? Really what we're trying to measure is what kind of energy is that stored as now. It starts with an E, the elastic potential energy, okay? The energy of the spring is kind of how we shortcut symbol that sometimes, with a little I for initial, okay? Then as it pops open, it flies off the table. It does turn into kinetic energy, but we're not worried about this KE right here, okay? It's transformed to KE, but in the end, at the very top, when it stops moving, what does it all turn into? It all turns into gravitational potential energy. You see that? Okay? And you're saying, man, that's totally lame, because you're a really bad artist, Mr. Lau. Yeah, I'm just, sketching out. But what it is we're trying to picture the energy. The math is easy. Multiplying, dividing, adding, subtracting, big deal. You could do that in like 7th grade, whatever, right? It's the ideas, the physics part. That's what we're trying to focus on. Okay? Now, that's the simple method. Some of you guys did the little bit more complex technique because you're more coordinated than me. Okay? And it's the more fun way, which is you flex it, but instead of starting on the table and trying to hit it with your pen or pencil, which also takes coordination, and I lack, you started a little bit higher off the ground. Why is that a little bit more complex in terms of your energy analysis? If you start off this up here above the ground, not only do you have elastic potential energy, energy of the spring initial, you have to add on what, since it's off the ground? A little bit of potential energy, right? Because it has a certain initial height off the ground. Okay, so if you did that, you have to add in that energy. No big deal. You drop it, it hits the ground, and then boing. Does it bounce to the same height, or did it bounce higher? Aha, right? It bounces what? Higher, right? And why does it go to a higher final potential energy? Real easy to see, right? Because that's the whole point of the pop-up toy. You stored up extra energy in there, yeah? Okay? And that's kind of the idea behind designing athletic shoes, to try to have shock absorbers in the heel. There's a company, I think they're called Spira. I think, are they German? I don't know. And they have like these funky like wave springs in their shoes. And I think they were actually banned from certain marathons because their shoes gave the runners too much advantage. Okay? So when they first came out, I think they hired some Kenyan runners to wear them. They're like these bright yellow fluorescent shoes. I don't know if you've seen them. Okay? So it's just kind of interesting how science and technology start to collide to transform a sport. So anyway, once you picture it, it's actually not that bad to solve the rest there. This is actually step 1 and 2 is the hardest part. Okay? So now we're going to move on to step 2. And Colin, you group, you guys are going to volunteer your data, right? Yep. Which method did you guys do? Did you guys do the drop it method or the pop it from the table method?
We did the drop it.
You did the drop it method, the more complex one. That's cool. Okay? It doesn't matter which method you do. You just have to be consistent in how you identify your data and you list your information. Okay? So why don't you give me your group's data? Tell me what you guys measured. And the trick is, I want to see this for everybody. If you didn't do this in step 2, fix your calculation, okay? Remember when we did projectiles, we separated it into what? An X and a Y. For forces in 2 dimensions, also X and Y, or if it's on a ramp, perpendicular parallel, right? So for energy, you want to have an energy initial and an energy final, okay? That's how you set up your energy equation. So at the very start, give me some of your data there. Go ahead. Okay, so you dropped it from 1 meter high towards the ground, and then what did it bounce up to? What was your final height?
1.42.
Okay, 1.42. That's cool. So it looks like you got an extra 42 centimeters in your bounce there from the elasticity of your pop-up toy. Cool. Give me your other data.
The mass was point, or 0.0193 kilograms.
Okay, and good job. A common mistake that I noticed when I was helping some people yesterday is that they forgot to convert grams to kilograms, okay? So everything should be in standard metric units. And the mass shouldn't change because it's not like your pop-up toy blows up and loses parts, okay? Good. When we go to Great America in May, awesome field trip. That's the whole point. You're transforming energy, and mass should not change unless you lose like a flip-flop on your shoe, or hopefully nobody loses their cookies or funnel cake. Or it always gets me. There's always one kid who gets one of those big turkey legs, like at 10 in the morning, and they're standing in line for the Batman or the Raging Bull, and I'm like, yeah, I'm not going to stand behind you. There you go. Okay, next. Let's keep it moving. What other data did you collect? Anything else? No? Okay, that's okay. So let's think about it. At the very start, you also did what? You needed one more piece of data. You flexed it, okay? You stored up some elastic spring potential energy, which is 1/2 kx squared. You're trying to find k. That's the whole point of this problem. Make sure you list your unknown, okay? And you know what? You're right. Like, I don't know what information I need to list or not list. That's why your picture helps you, okay? To think about the energy you're trying to measure or store up. And then the last thing you needed to measure was the x value, okay? Did you guys measure that or you forgot to? How much you flex your pop-up toy. Measure that? Oh, there we go, okay? That's okay, because the toys are all the same. Someone else want to give me that value? How many meters or centimeters? Yeah, what'd you guys get?
We got 0.04 meters.
Okay, yeah, it's about 4 centimeters altogether, which is 0.04 meters, okay? Does it make sense? How much you're stretching your toy there. Got it? Okay? Good. Next, we did the hard part. This was the stinky part, okay, was setting this all up. If you did the first method, your energy equation is going to be a little bit simpler, okay, because you started on the ground. You guys chose to do things the crazy way, which is no problem. And all that is the energy you put in is the energy you get out, right here in step 3. And how do you write your energy equation? The trick is you look at the picture, okay? You're visualizing the energy you put in. In this case, it's the flex of the pop-up toy, the energy of the spring, plus its initial potential energy lifted off the ground. And when it pops up to the very peak, that's what's nice. That's why you pick its highest point. All of that energy then is converted into potential energy final. So now we can expand our energy equation. The energy of spring is 1/2 kx squared. It looks like the kinetic energy equation, but it's the flex of a spring times its springiness, okay? Plus potential energy, mgh initial, is equal to potential energy final, mgh final, okay? And now it's a basic algebra problem. It's just plug and chug. You want to take all of your info from step 1 and plug it all in, okay? So what do I put in? I put in 1/2 k, that's what I'm solving for. X is 0.04 meters, don't worry about units, squared, plus mgh initial. The mass was 0.0193 times the g value of 9.8 times the initial height of 1, so that makes it easy, and that's equal to, on my right-hand side, mgh final, which is 0.0193 kilograms times g, 9.8, times my final height of 1.42 meters, okay? So now I'm just going to get my calculator and do a lot of plugging and chugging, okay? You do your numbers, I'll do this sample set here. I'm going to do the right-hand side of the equation first, so I can figure out the total energy of the system. 0.0193 kilograms times gravity is 9.8 times a height of 1.42 meters, and that's like 0.269 joules of potential energy at the end, okay? So if I want to get this elastic energy, I just found this right here, okay? And if I want to figure out what's my spring energy I put in, I just need to subtract out the initial potential energy. So I'm going to subtract from that mgh initial, which is 0.0193 times g, 9.8 times the initial height of 1, and that means 0.07943 joules of energy went to my elastic spring potential energy, okay? 1/2 kx squared. So to get k by itself, all I do is I'm just going to multiply both sides by 2 and then divide by 0.04 squared, okay? So all I'm doing is a bunch of crazy algebra there. if you have a hard time doing this in your head, just write out each step. I'm just out of screen space there, okay? So if I divide that by 0.04 squared, making sure I don't screw up order of operations, I get a K value of about 99.2 something. There we go, 99.3. We'll do that. K equals 99.3. And the units for K is newtons per meter, okay? So what does that mean? It takes, in this case, almost 100 newtons of force to stretch it an entire meter there, okay? Now we're ready for part 2, okay? Now what we're trying to do is we're trying to find the initial velocity, the launching speed of the pop-up toy off the table. Common misconception is that the initial speed is 0. Well, that's silly. Like, we know it's 0 when it hasn't popped off the table, right? But of course, once it leaves the table, it's moving, right? Another popular misconception is if you drop something from a building and it hits the ground, its final speed is 0. Well, it's 0 after it hits the ground and stops, but I guarantee you, if you jump off the building, you don't hit the ground at 0. Don't do that, okay? So here we go. Step 1, it's all about your what? It's all about your picture, okay? And all it is this is pretty simple. The energy that you put in at the beginning, right here, when it pops off the table or the ground, it's going to fly off, right? And you did some kind of work, some kind of elastic potential energy, but really the key is at the very beginning, okay, we're looking at the kinetic energy that it launches at, initial, okay? And then as it flies into the air at the very peak, it all turns into what? Potential energy final, okay? That's the only energy we're concerned about, okay? Though I know some of you guys, you started it off here, okay, and then you dropped it, and then it bounced. But we're just going to pick this point as our starting point, launching from the ground, okay? And you're saying, I don't get it. How does that picture help? Well, all it is that's your energy equation right there, okay? So now in step 2, we just break down our info as before, but the key is how many columns? We want to have 2 columns, okay? So at the very beginning, it's launching off the ground. It has some kind of kinetic energy, right? And our whole point is we need to find that kinetic energy so that we can determine the initial velocity in meters per second. By the way, one person I was helping noticed that you can actually solve this using nifty equations, which is cool too. You know what's funny? You get exactly the same answer. But I don't want you to do it with the nifty equations. I want you to do it with energy because energy is a lot more elegant. Because later on, when we look at something more complicated like a roller coaster track, roller coaster's annoying because the track changes all the time, and then how do you figure out the force, parallel, whatever? What a mess. But from an energy point of view, it's very elegant. The energy you put in to a system is energy get out, okay? So there's some kind of kinetic energy we put at the beginning. The mass was the same as before, which was, let's just take a quick look-see here, 0.0193 kilograms. And then it goes to my final state of potential energy. So this doesn't change, 0.0193 kilograms, which is just mgh final, right? And the final height that you guys had it pop up to was, let's take a look-see here, 1.42 meters, okay? So we can figure out how high it pops up is the energy that we get out, which is the same as the energy that we what? Put in, right? So in terms of our energy equation, this is a very simple energy transformation. All it is the kinetic energy of the pop-up toy leaving the table all goes to potential energy at the peak. You have 100% energy transformed there, okay? So now it's pretty trivial. We just have to expand our equation. Kinetic energy is 1/2 mv squared initial is equal to potential energy final, which is mgh final. And now we can just substitute in our information for our last step here, step 4, okay? So if I take 1/2 the mass of 0.0193 kilograms, don't worry about the units, we'll put that on at the end, times the initial velocity squared is equal to mgh final. 0.0193 kilograms times gravity, 9.8, times the final height of 1.42. Okay? Anyone notice something very interesting before we plug and chug? What actually cancels out? The mass, okay? So a lot of times, mass will cancel out, other than if you have work or spring energy, because then that depends on the force you put in over that distance, okay? So in terms of like looking at energy, what's kind of neat is for a roller coaster, theoretically, it doesn't matter the mass of the riders, because a heavy object, a light object, they fall same, okay? So now we just plug and chug, right? On the right-hand side of the equation, we take a 9.8 Multiply that sucker by 1.42. Then to get VI by itself, we need to get rid of that half by multiplying by 2. And then how do you get rid of the squared? You take the square what? Square root there, right? And we're getting about 5.27. Okay, whatever. So maybe 5.28 meters per second. And if you think about it, that's pretty reasonable. It's leaving the table a little bit over 5 meters per second. Okay? So to summarize, the key to solving these problems is it's all about picturing the energy before and the energy after. Okay?